Let's make a simple throwaway processor just for the fun of it. It might not be super useful, but it will make us understand several things, like what exactly happens when we run a program, what machine code and assembly are. Precisely, we shall understand the layer between hardware and software. Then we design a hardware, and by the end of it, we'll make the processor and write its Verilog code and run some basic tests on it. There exists a similar video in Urdu. I'll share the link in the video description. Let's start with the basic building blocks and their Verilog codes. If you know what RTL and Verilog means, just skip this section by clicking the time tag in the video description. There exists a more detailed video about Verilog that I have linked in the description, but here is a quick overview. All digital circuits are made up of gates, and all gates take binary values as input, that is either 0 or 1, and they produce a binary output, either 0 or 1. An AND gate outputs 1 if all of the inputs are 1. If any one of the inputs is 0, it will output 0. In Verilog, we can write code in always block like this. For AND, we use ampersand symbol just like in most programming languages. Here A is output and B, C and D are inputs. An OR gate outputs 1 if any one or more of the inputs is 1. It will output 0 if all of the inputs are 0. So any input 1 means the output will be 1. For OR, we use this bar symbol just like in most programming languages. An XOR or XOR gate is called exclusive OR. It's similar to OR with one difference. If there are two inputs, then it outputs 1 if only one of those inputs is 1. In other words, we have 1 exclusively at one of the inputs. If both of the inputs are 1, it will output 0. For more than 2 inputs, it acts as an odd parity gate. But let's skip that. Google it if you like. We use gap signal for XOR gate, and that's it. A NOT gate flips input, that is it outputs 0 if input is 1 and outputs 1 if input is 0. The next building block is a mux. A mux is a selector. That is, it selects among multiple inputs. It connects one of the inputs to the output. The select line or address selects which input is to be connected to the output. We use case statement for this. Here, if the select line is 0, input A will be connected to the output. If select line is 1, B will be connected to the output, and so on. Demux is kind of inverse of a mux. It connects the input to one of the outputs and connects rest of the outputs to 0. We can use a similar case statement, but let's skip that part for now. We shall see a little bit different syntax too shortly. An adder adds two numbers. Those numbers can be n down to 0. Output typically has one extra bit. Similarly, a multiplier can multiply two numbers. The output width is generally double as compared to the input. In Verilog, we use plus for addition, minus for subtraction, static for multiplication. A register is used to store bits or numbers. It runs on a repeating square wave called a clock. It often has a reset signal on which we can give the register some starting value. At rising edge of the clock, we sample the input and store it as shown. Here 3 is stored on the rising edge of the clock. On next rising edge, 4 is at the input, so it is stored, and so on. We often have an additional enable signal as well. The input value is stored only when the enable signal is high at rising edge of a clock. For example, here's some unknown prior value of x which was already stored, will remain stored in the register until we have an enable signal at the rising edge. In that case we shall store whatever is at the input. In this case it's 5. In Verilog we use an always at POSIX clock block to code registers. Also, equality signs are a bit different. These are called non-blocking assignments. The syntax is simple. We assign 0 or some starting value in case of reset and assign the input value otherwise. In case there is an enable signal, we can use else if instead of else and use enable there. Let's do a quick example of a regist file. Register file is an inherent part of most processors. We have a bunch of registers and we want to read and write those. For reads, we provide an address signifying which register number to read. Pause the video and think of which component can be used here to read. Well, a mux can be used here to do the selection job. For writes, we want to write data into a specific register specified by the address only if write signal is 1. Pause and think about it too. Well, we can broadcast data in to all the regis inputs and demux the write signal to all registers enables. Since demux will ensure that write is passed to only one of the regis, enables of all other regis will be 0. That is, no data will be written on them. And data in will be written to only the register where write is forwarded using demux. We can use arrays as well in Verilog, and reading from an index of an array creates a mux, and writing at an index creates a demux like we used here in the regist file. So it's a short syntax as compared to the case statements we used earlier, but it is only valid for arrays. This reg file can also be thought of as a memory because a memory also stores data on some address. So it's a crude model of a small memory that we can use in our processor. We can encapsulate our designs in modules. Modules can be reused wherever we like. Here is the syntax to create a module. Let's say we want to create a FIFO in which we can push or pop data. We create a file named FIFO.v and write a module like this. We can write our Verilog code in module body. For inputs and outputs, we use keywords input and output. These are also called ports. If a port has more than 1 bits, like here, the data is 16 bits, we can write 15:0 and we read it as 15 down to 0. We can make it even better by using parameters. For example, use the parameter width instead of 16 here. Such params can be declared right at the start of module definition. Now, while instantiating the FIFO in our code, we can choose whatever value of width as we like, so this makes the code a bit generic. Parameters are extensively used in practice to make code more flexible and generic. So now let's dive into some processor designing. Normally when we write some code in a higher level language like this, it gets translated into a series of instructions to the processor. Here we multiplied register x1 and x2, storing values c and d, and saved the result in register x4. Then we added x4 with x0, which was storing b to complete the calculation. And then stored the result in x3, which was representing a variable a. Generally, the variables are stored in some memory. We can call it data section of a memory. So we need to fetch them from the memory. The instruction to fetch data from the memory is called load word or LW. We provide a memory address and which register we want to load value to. For example, here we load B, C, and D from memory locations 1, 2, and 3 to regis x0, x1, and x2. Similarly, at the end of computation, we store value back to memory. The instruction used for that
store word, which in this case stores register x3 to memory location 0. Location 0 is signifying variable a. So this is our program. It is typically stored in a section of memory called program section or text section. Instructions execute one by one till the whole program is completed. This type of code is called assembly code, but the processor cannot understand such pseudo English. It works on binary, so we convert it to binary called and that conversion, the code after conversion, the binary code is called machine code.
So whenever we run a program on a computer, so there is an executable file in Windows. All the files with extension .exe or exe files are basically this kind of machine code. So now let's dive into some processor designing. So let's say we want to make a processor. So we know that we'll have some program memory and data memory and register file. But let's say these are the instructions that we want to support. So we want to support two kind of instructions. This is the first kind. So firstly, we want to support instructions like add and multiply that we already seen. Similarly, let's say we also want to support subtract and AND operations. So they work like this, like if we say subtract x1, x2, x3, we'll subtract x3 from x2 and store its result in x1. So these x1, x2, x3 are representing the registers in the reg file. Let's assume that we have 32 registers and each register is 32-bit wide. So that will make things simpler. We added NAND here because NAND is a universal gate. We can do all the other gates using NAND. You can Google it up too. And in addition to that, we also saw the instructions of load word and store word. So let's say that we only want to support these 6 kind of instructions. So first of all, we want to convert this pseudo English to a machine code. So for that, we can assign a number to each kind of instruction. For example, we can assign 0 for add, 1 for subtract, 2 for multiplication, 3 for NAND, 4 for load word, 5 for store word. So this is often called opcode or operation code of the instruction. Now we want to define a binary format for these. For add or subtract or multiply or NAND, firstly we need to have some opcode field. So in this case, we have 5 instructions and 5 is 101 in binary. So we can have 3 bits for that. But we can assign, let's say, 5 bits just in case that we want to extend our processor in the future. So we have assigned 5 bits for the opcode. So we can have 32 different combinations of the opcode in this way. Then we also need to specify 3 registers. 2 registers are the registers that will be read from the regist file that will be used in the computation. We can name them source registers. And 1 register is the destination register where we'll write the result. So we can, since we assume that there will be 32 registers, so we can number them from 0 to 31. And 31 can be represented in 5 bits of binary. So that's why we have assigned 5 bits for destination, 5 bit for source, source 1, 5 bit for source 2. So if we have an instruction of add x1, x2, x3, we can simply use 0 here, x1, 1 here. For x2, we can write 2 here and 3 here. And similarly, for subtract, multiply, and NAND, we just need to change the opcode. For load word and store word, we can also define a similar pattern. The opcode will remain the same at the same place so that we can always figure out which instruction it is. For load word, we need a destination register and a memory address. So we use the same dest field that we used in the ALU instructions above, and we used lower bits as memory address. As for store word 2, we require a register that we want to write to the memory. So we use the same source 1 field here as a source register and use the lower bits as a memory address. You can think of it, you can ask why I haven't used this area for store word. It will simplify hardware a little bit as we are making a throwaway processor. So we can go get away with the simple hardware. Okay, so these are three kind of instructions that we are supporting. Now we can jump to the hardware design. So we already saw a register file, but in our case, we need to read two registers. So we know that we need to read two registers at the same time and then add, subtract, or multiply those. So for reading two registers, we can add another mux. So another mux can read from a different address and output data at both addresses. We already separated address into write address and read address so that we can at the same time write to an address. So the destination will be written using the write address, the sources will be read using the read address. Equipped with this two-port or rather three-port reg file, two for reads and one for write. Now we can dive into the detailed design. So these are the kind of instructions that we are supporting. The first thing that we want is that we want to get instructions out of the program memory one by one. So we have seen that memory is just like a reg file. It has address, data, and write ports. So in program memory, we don't want to write anything. We just want to read it one by one. So that can be simply done by having a counter. So this counter increments the value in this register in every cycle. So this kind of counter is generally called program counter or PC. So since it will be incremented one by one, so we'll get the data out, which in this case will be our instruction. Let's say we want to make design for only ALU instructions. So for ALU instructions, this phase of instruction getting from the memory is called instruction fetch, and we want to read two registers based on these fields of the instruction. So we already have a reg file with two read ports. We can connect the source 1 and source 2 ports with the address ports, and we'll get the data out of reg file for those two registers. Then we want to add those numbers or subtract or multiply or NAND, whatever we want to do. So before doing that, this phase is sometimes called decode and sometimes it's called operand fetch. These two numbers that we are fetched are called operands. Now to execute those add, subtract, or multiply, we can actually just give it input to an adder or subtractor, and it will output the addition or subtraction. And similarly, we can give it input to a multiplier and an AND. So we can give it input to all of those. And then we can select based on our opcode which output we should take. So for selection, we can use a multiplexer. So here I have used an adder subtractor because in practice we can use do 2's complement arithmetic to do subtraction using the same adder. So so we have the result of this ALU instruction and we want to write it back to the reg file. So this phase is called execute phase of the instruction. Here we do the actual computation. Then we want to write back the results, and this phase is called write back. And we want to write back the result to the register file, but I'm drawing it again here. So it's the same register file, but I want to show the phases of the instructions. So this last phase is basically writing back, but I'm showing it here. So to write it back, we can connect the output to data in, and we can use this dest field here as a write address of the reg file, and we can write we can have the write signal as 1. So this will write this output to the REG file. So by adding these components, we can actually support all the ALU instructions. In all ALU instructions, two registers will be read. Then we'll perform all of the operations, but based on opcode, we can select the output of the right operation, and that output will be fed to the REG file. So this is the write back or write results phase of the instruction. Okay, now we want to support the load word instruction, and for that we have a data memory. And data memory, as we know, has this ports address, write enable, data in, and data out. So we already know where to connect address. These lower bits are of the address. So from this address we'll get the data out, and we want to write that data in the REG file. But in our REG file we only have one write port. But we also note that if the instructions is load word, then we are not using ALU result because it's a load word instruction, and if it's an ALU instruction, then we won't be using the load word side of the things. So we can select between the two, and whenever we need to select between the two, we can add a multiplexer. So we add a multiplexer here, and as soon as we add a multiplexer, we also have a select line that we represent as CTL2, CTL2 as control 2. So so we can create the signal by comparing opcode with the opcode of load word, which in our case was 4. So if opcode is equal to 4, then we'll take data from this side. Otherwise, we'll take data from that side. Now, similarly, for store word, we want to read a register and write it back to the data memory. So we want to connect it to the data in port, and we already know that this source 1 field is reading from here, so we can connect that to data in. And in case of store word, we need to enable this write enable as well. So we are representing it as CTL3. So control 3 can be generated by comparing opcode with store word. But this also adds another complication, that in case it's a store word, we don't want to write in the REG file because store word is writing from register to the memory. So this one should not be 1 for store word. So we can call it a CTL1 signal or control 1, and that could be that if opcode is not equal to store word, that either it is load or some ALU instruction, then we write to the REG file. So that's it. That makes the whole processor. Just by adding a couple of muxes and a counter, we are able to make a small processor that can carry on the 6 instructions that we chose. Okay, so now let's move to the Verilog code for this processor. So we can write code for every block. For example, for the REG file, we have this kind of logic. So we can declare regs as an array that we have a 31 down to 0. This is the width of the every element array, and 0 to 31 means that we have 0, 1, 2 up to 31 regs, 32 total because we are counting from 0. To read, we can just use an index from the array, as I already told that it will make a mux. And for write, we can use an always at posage clock block, and if write enable is 1, we can write to that specific address. This will generate this demux structure for the REG file. This is a simple counter. So we already know that we can use always at posage clock to generate a register, and we can increment that register based on every clock cycle. So if when we come out of reset, we can start incrementing it. The ALU side of thing can be written as this. We can extract the opcode out of it using always at static opcode is equal to this these bits from instruction. And then we can use always at static and create a case, so that will create the smux. And the least significant bits, that is, if these are 0, then we are adding. If it's 1, then we are subtracting. If it's 2, then we are multiplying, and 3, then we are using NAND. So here we have used add, subtract, multiply, or NAND. So here we haven't used the adder subtractor, but it's a simple code, so we don't want to complicate things in this demo. Otherwise, we can have a single adder that can do both of the things. So this mux can be coded using an if else or case as well, but I also wanted to show an alternate syntax. This syntax means that if control2 is 1, uh, take data, take this thing and assign it to this thing. And if it's 0, then take this thing and assign it to this thing. So ALU out signal is this one, and DRAM out is this one coming from data RAM. So we can, if control2 is 1, we select DRAM, otherwise ALU. For data mem, we can use, so here I have instantiated a template module that is given by various FPGA vendors. So in case it's a BRAM module from Xilinx, I have a separate video for that. The code is very similar to reg file, but here I have instantiated the module. So just like we created a FIFO, we have already created a BRAM. So when we want to use it, we write BRAM and give it a name, and then we connect its ports with our signals. So here we created the connected clock with clock, and we always enable it. So we have connected it to 1, and we have connected write enable to control 3, just like this, and address to instruction 8 down to 0 in this case, because we are using a smaller BRAM. Otherwise it was 16 down to 0. And uh, input data is connected to this operand 1, and output data is connected to the DRAM out signal that is also used in the reg in this mux. And similarly for program memory, we can have a similar instance, but in this case the address is coming from program count, and we are never using the write enable or input data. So this specific template can be initialized with some initial data as well that I'll show shortly. Okay, so here is an example of the code we already discussed. I have created this file processor.p with the code in the slides. So here we can see the program counter and then the program RAM and reg file and ALU muxes and block RAM and control logic in the end. So I probably didn't mention in the slides that when we want to instantiate a module, for example, here is the reg file that we discussed. So it's a module with read address 1, read address 2, and write address. So if we want to use it in our processor, we create code like this. So we write the name of the module, then the instance name, and then we connect the ports. Like here we connected clock with clock, read address with instruction, the relevant bits of the instruction as shown in the slide, and so on. So this is the complete code. For the block RAMs, I have used some template code that is provided by Xilinx. So I have another video explaining that, how to use it. These parameters actually can configure the size of the block RAM, and we can select a file that can instantiate the block RAM. That can actually fill the initial data of the block RAM. So that's the code. But to test it, we generally have to write a test bench that I haven't discussed in this video. You can go to the Verilog video in the link description for understanding how to write a test bench. But in this case, it's a very simple test bench. So here is the test bench where we have instantiated the processor, and we have told what file to use for program and what file to use for data. And we generated a clock, and we just waited for 30 cycles after giving some initial reset. So if you don't understand this code, it doesn't matter at the moment. You can read about the test bench later on. So to test this out, so this is my folder um, where I have these files, the test bench, reg file, processor, block RAM, and the data file that can be used to initialize the memory, and program file that is used to initialize the program memory. So these files are kind of here. You can see that this is our program file, and in hex format. This is the program in assembly format. It's a little bit different than instead of x1 x0, here it's r1 r0, because I'm using an assembler that was written by one of my students, and I'll share the whole source code including the assembler. So it's a C++ file which actually takes some inputs and generates the assembly file, and takes input as assembly file and creates a hex output. So but that's not in the scope of this video. So this is the assembly that we already discussed. These are the data memory values. The B, C, and D values are here, 2, 3, and 5. And this is the test bench. So I'm using a simple tool, Verilog. It's a very small tool that you can install. I'll put link in the description how to install that. So I am in the folder. So what we can do is we can go to the folder and right click and open in terminal, and this terminal window will open. So here I can compile using this command, verilog -o, and I give output executable name, and static.v means compile all the Verilog files. So it will automatically compile them and create an output tbproc.pvp. So once it's there, I can actually run it using a command pvp /tb underscore proc.pvp. It will run the test bench and create a wave file dump. Here we can see that it has created a wave file dump. We can add prints there in the test bench. I haven't added any. So typically what hardware designers do is that once their initial tests are running, they want to see the waveforms, and for that there's a free utility that can be used. So for example, that's called GTK wave. So I have when we ran it, it created a wave file, wave.pcd. So I can open that using GTK wave. So this is the waveform view, and I can add this all the symbols in the waveform window, and I can maybe zoom in. I don't know if control maybe. So here we can see that OP1 and OP2 were the operands that were coming. So if I maybe I can convert it to decimal, then you can see that we initially we read 3. So what we wanted to read was here is the our data file. So so we have 2, 3, and 5. So we wanted to multiply 3 and 5. So 3 into 5 are 15, and then we wanted to add 15 with 2. So here we can see that 3 and 5 were first loaded, and then we read 3 and 5 and multiplied it and stored it result. In the next cycle, the result 15 was added to 2, and the next cycle 17 was stored. So when we store it, the write enable, which is control 3, this write enable was asserted for one cycle. So it seems that processor is running fine, and we have stored the values. We have run the program, and it stored the values. We have a lot of access afterwards because our processor keeps running. So it's a crude processor. We haven't have any mechanism to stop it at the moment. So now that we have created the processor, a simple processor, we can make it a little bit fancier. If we want to do some realistic workload on this processor, we'll need support for conditional statements like if-else, where we can check some condition, and if it's true, we run this piece of code. If it's false, we run some other piece of code. And when we are done with this piece of code, we want to jump unconditionally to some other place. So this is one kind of instruction that we want to do. In addition to that, we want to support loops where we want to check conditions, but we want to jump backwards from here if that condition is true and run the code again. So there are a couple of type of jumps or branches that we want to do. One is that we want to unconditionally bypass some piece of code. Another is that we want to check on some condition. So for checking conditions, we can actually use our ALU. For example, if we subtract a number from another, then we can actually, if the result is 0, it means that both numbers are equal. If it's positive, then A was greater than B, and if it's negative, A is less than B. So we can add a few more opcodes for branch not equal to 0, branch equal to 0, and branch positive to support different kinds of checks on that. And we can actually make a convention that we always write its result on register 0, and based on that register we can make decisions whether we want to jump or not. So we want to add two kind of jumps. One is unconditional jump, where we don't check any condition. Like here, if code was executed, then we want to bypass this piece of code. It's easier. We instead of adding 1 into the program counter, we want to add some offset that can be taken from the instruction, and the hardware will change in such a way that instead of adding 1, we could either add 1 or this offset in this adder that can be added to the program counter. And we'll have some control signal to control that. If the opcode is of jump, then we use this path, otherwise we keep adding 1. For comparing with based on register, we can actually read from a register and jump on that specific value instead of that adder, and then this way we can basically jump based on a register. Okay, so here this is the opcode for jump based on register, and we supply the register in this source field that we were already using, and we use that register to jump to a specific register value. So jump based on register is used for another use case, and this case is like this. So here we're calling factorial a couple of times, and here is the code for factorial. So when we call factorial from here, we jump to the factorial function, and then we want to return from the function and come back here right in the next instruction from this line of code. After a while, we want to calculate factorial again, and we jump again to the factorial function, but we want to return back to the instruction next to this instruction. So the same return, how can we use it to jump back at times here and at times here, and if there is another call, then to that place. So this can be done if we can save the program counter in some register at this point in time when we were calling the function. And this is generally done using jump and link instructions. In jump and link instruction, we generally fix a register that we used as return address. For example, we can, let's say, fix register number 1 for that, and we always write program counter to that whenever there is a jump and link instruction. So if the opcode is jump and link, we write the program counter +1 value here in the return address. So while jumping from here to factorial, it will be just like normal jump, but the opcode will be jump and link instead of jump. So we can jump the same way, but at the same time, the program counter will be saved in the register 1 or whatever register we have assigned. And for coming back, we can use this jump based on register instruction that will load the same register in the program counter. So we already saved the incremented value of PC. So now we can come back to that after the function returns. So if we call from here, PC +1 will be saved in the register. So when we jump based on register, we come back here. If we call from here, then this PC +1 will be saved, and when we return, we can come back here. So by adding JAL, jump and link, and jump based on register, we can actually have function call and return support as well. So in addition to that, it's very useful to at times have immediate values. For example, instead of adding register 1 and register 2, we can add a register to a constant value, and that can be supplied in the instruction. So for that, we can add a mux here, that instead of reading from data 2, we can take the value from the instruction directly and use that in addition, subtraction, or multiplication. So basically, we have added a few muxes, one for jump based on register, one for immediate instruction, and that will and the support for jump here. So by adding those, our instruction set has increased a little bit. So now we can support add, subtract, multiply, and load word, store word as earlier. But we can also use branch instructions that can always compare with register 0 value, whether it's 0, not 0, or positive, and jump based on that. And these can be used to support if else or loops. And then jump instruction is also required for bypassing a piece of code, like after the if statement. Jump register and jump or JAL, these two can be used for function call. And add immediate and similarly subtract immediate, multiply immediate, and add immediate can also be used for immediate instructions. So it will be a good exercise if you can use these instructions, and you can add these instructions to the base code that I've provided and try those out. Now that we have an idea about how to design a processor, we have seen that if we make our processor from scratch, we'll have to write its own software as well. So I have shared the assembler code as well, but it would be better if we could have a compiler as well, and writing that would be a challenge in itself. So instead, it would be better to start off with an architecture that has all these tools available. For that, we can use probably maybe RISC-V processor. So RISC-V is an open source processor, and here is the instruction set of RISC-V's simplest core, RV32i, which only supports integer instructions like us. So here you can see that we have to support a bunch of other instructions as well. So it's kind of similar, like add immediate, and immediate, add upper immediate to program counter, branch equal, branch greater than equal, branch greater than equal to unsigned, less than unsigned, a bunch of branch instructions. Some atomic instructions that are used for basically synchronization between multiple threads that are important. Um, then jump and link based on registers. And then there are a bunch of instructions to load bytes and load half words. So we often use characters and that are not complete words. So we want to be able to load a byte and half a word like that, or immediate. Similarly, store byte, store half word. There's some shift instructions which shift the contents of a register left or right, and there are variants with arithmetic and logical shift, uh, and then subtract, store word, and XOR. So this is the kind of complete instructions that is supported. So I'll share a link to this document as well. This is a very good document that explains what exactly happens on these instructions. Loaded with your knowledge about processor design, you can actually see how these instructions are interpreted. So I'll just, let's say, for example, take one example. For example, branch equal. It compares two registers, and if they are equal, it adds this immediate value to the program counter. But this immediate value is distributed in different places. So you can click here, and this will tell you how these bits are computed and how immediate value is computed. So I'll put a link in the video description, and if there is interest, I can cover RISC-V assembly as well. And in addition to that, we just created a basic processor which didn't have any pipelines or caches. So that are some other topics that can be covered, and I'll try to cover that if there is interest.